Looking at the section 6 examples, and these are all going to be proofs. For our first example, we are given that BCDA, the shape right here, is a rhombus. There's a whole bunch of properties that come along with that. We're also told that BA is equal in length to CE. And our goal, the thing that we want to prove, is that CDE is equal to E. So this angle here is equal to CDE, this angle right here. So our goal is to prove that those two blue dots are the same. We are given a rhombus. Now, if I'm going to write out this proof, and this is a proof where it doesn't have any fill in the blanks, so I get to pick my own path, which I actually kind of like, and I think it makes it a little easier. I'm going to mark in another color all the things that I know about rhombuses that I think would help me. My guess here is that if I'm trying to get two angles of a triangle to be the same, I know I'm going to have to get an isosceles triangle. And so somehow I want to prove that these two are the same length as each other, especially since I have one of those side lengths and I think I can get the other. That would be one good way to prove that those angles are the same. So as I look at my rhombus, I know that this side and this side are going to be equal to one another. And if those two sides are equal and then the two green sides are equal, by substitution I can get that the two outside or that these two in this triangle are equal to one another. So let's go ahead and work it out that way. I start every good proof with my given. So I have my given right away. Let's zoom in here. And by my given, I get that I have a rhombus. And I also know that BA is equal to CE. So I can write all of that right away. And then my next piece of information that we are going to get right away was the two sides I marked in red, that CD is equal to BA. So BA is equal to CD, and I got that by one of the properties of a rhombus. So because I had a rhombus and I took something that I get from knowing a rhombus, then I can just declare it by property of rhombus. Now let's do that substitution step. So by substitution, I'm going to get the fact that, well, these are the same, so CE is going to equal CD. So now I've gotten to the point in my proof where I've proven that CE here and CD here are the same. So now I can prove that the angles that they're a part of are also the same. I can prove that angle CDE is equal to angle E by isosceles triangle theorem. So once I have the two sides that are congruent of an isosceles triangle, I get the two angles that are congruent. And that's it. I've already made it to the end, so I'm moving on. Next example here, we have fill in the blank style proof, so we need to kind of follow its pattern. We don't get to make up our own plan, but we still should explore and kind of see what the picture can offer us. We're given that angle 3 is supplementary to angle 2. So this angle here and this angle here add up to 180. We're also told that angle B is equal to angle 3. So this angle right here is the same as this angle right here. We want to prove that we have a parallelogram. So we want to prove that we have parallel sides. We want to prove that we have equal length sides, equal length, parallel, parallel, and so forth. So clear that off there. Now, one of the things I see from this picture already is these two angles, right here and right here, are alternating interior angles. and since they're equal, that's going to give me parallel lines. So I'm knowing already that I can make these two lines parallel by alternate interior. So that's one good step towards proving a parallelogram. As far as other things, I know that I have 2 and 3 being supplementary, and so based on that, I can probably find some other interesting things along the way, possibly something to do with 1 and 4. But let's see kind of where the proof starts us off. So at this point, I think we have enough to get started. Our second step is that alternate interior angles implies parallel. Well, that was one we were just looking at, about the angle B and angle 3. So we're going to get AD and BC as parallel. Next thing says that something's true by the definition of supplementary. Well, lots of things are true by the definition of supplementary, but since we don't have anything so far, I'm guessing that it's going to be going back to our given, that angle 2 plus angle 3 equals 180. Because that's the only thing that we were told was supplementary. So let's try that. 3 and 4 here equal 180. Well, we know that that's true because that's a linear pair. So we would put definition of linear pair. Since 2 and 3 equal 180 and 3 and 4 equal 180, they do in fact equal each other. And since we have substitution, and that's the only things that really plug into each other, it probably has to be our only option at this point. So these things are made equal, which means that angle 2 plus angle 3 equals angle 3 plus angle 4. Next step, subtraction. Well, we see that we have angle 3 on both sides here, so if we subtract that away, we get that angle 2 is equal to angle 4. And by the way, now that that new information is given to us, I want to put that in my picture right away. So angle 2 is equal to angle 4. That's good to know. Next step, we're told that AB is parallel to DC. So AB is already made parallel to DC. Looking at the angles that we just got, I would guess that we have corresponding angles that are equal that made those lines parallel. So that would make sense. So we could say that corresponding angles being equal gives you parallel lines. So a lot of symbols here, but corresponding angles are equal. That gives you parallel lines. So that's what we wrote there. And then the last step, we have a parallelogram. And whenever you get a shape, it's by the definition of that shape. So definition of parallelogram. Because we proved this side and this side were parallel earlier, now we prove that those two are parallel. And two sets of parallel sides is enough to prove a parallelogram.